Hello everybody. In this video we're going to cover section 3.3 of our textbook where we're going to describe the fundamental properties of solutions. We're going to calculate solution concentrations using molarity, and we're going to perform dilution calculations using the dilution equation. So far we've been talking a lot about the composition of pure substances. However, there are very few pure substances that we interact with on a regular basis. Typically, we're going to see mixtures, which is where we're going to have one or more pure substances mixed together. All right. But similar to pure substances, we still need to have some sense of the relative composition of a mixture, because it's going to play an important role in determining its properties. All right, so knowing how much of each different pure substance is in the mixture is going to determine what that mixture looks like and how it behaves. There's a lot of different examples of mixtures. One example would be like coffee. In coffee, we have water, which is a pure substance. We have all of that plant extract from the coffee. That's just a whole bunch of different kinds of pure substances. We may add sugar to it and dissolve that in there. Now that's a component of that mixture. So even just something as simple as your morning coffee is really a very rich mixture of many different kinds of pure substances. There is a specific type of mixture that chemists are often very interested in talking about, especially initially, because we have a lot of good math that allows us to treat this type of mixture, and they're called solutions. Solutions occur frequently in nature, and they are basically a homogeneous mixture. And if we go back to the definition of a homogeneous mixture, this means that it has a uniform composition and it's the same properties throughout its entire volume. And chemists really like this type of behavior, right? That means that I can take whatever sample I want from the homogeneous mixture, and I know it's going to be the exact same as any other sample that I take from it. The relative amount of a given solution component is known as its concentration. Okay, so if I know the relative amount, not the total amount, but the amount that I have relative to the rest of the mixture, all right, that's its concentration. And we're going to talk a little bit more about what the components in the language are around solutions. So basically, a solution consists of two components. We have the solvent. This is the component with a concentration that is significantly greater than all the other components. So the majority of your mixture, whatever pure substance is the majority of your mixture, is going to be the solvent. Going back to our example of coffee, our solvent would have been water, because if we analyzed it, we would see that we have more water molecules, we have more water by mass than any other component in that mixture. A solute is a component that is typically present at much lower concentration than the solvent. So the things that we put into our solvent are our solutes. All right. A solution is only going to have one solvent because it's the one component that's present in a larger concentration than all the others. Okay. But it may have many different solutes dissolved in it. A solution in which water is the solvent is called an aqueous solution. Aqueous meaning water. All right. So an example of an aqueous solution might be distilled white vinegar. Okay, this is actually acetic acid dissolved in water. And you can often see that on the label here. It says reduced with water to 5% acidity. That means that 5% by mass of it is acetic acid, and the rest of the 95% of that is just water. And you can see, if you've ever worked with white vinegar, it has very different properties from water. It's a very pungent smell, very pungent taste, and that's only from the addition of 5%, a relatively small amount of this acetic acid. So now we're going to talk about molarity, and molarity is a very important type of concentration that we're going to see over and over again when we're working this year in this term, and it's going to come up over and over again, especially if you continue on in chemistry. So it's very important that you understand the idea behind molarity. All right. Molarity has a unit, and it is just this capital M. All right, which could be very confusing with things like moles and stuff like that. All right, so it's very important for you to recognize that capital M is going to be molarity. All right, and moles, when you write out moles and you give a unit and stuff, should always be written out MOLS or MOLES or something like that. You shouldn't just give it a capital M or a lowercase m. Those actually have different meanings in chemistry. And what a molarity is, it's the number of moles of solute, okay, so one of our components, in exactly 1 liter of the solution. All right, not 1 liter of solvent, but 1 liter of the solution, the total solution. So capital M is going to equal the moles of solute divided by the liters of solution. Molarity is very useful, as I've alluded to, and it's used in many applications in chemistry. So let's take a look at an example of a molarity calculation. A 355 milliliter soft drink sample contains 0.133 mole of sucrose, table sugar. What is the molar concentration of sucrose in the beverage? So a couple of things here. First off, we need to pay attention to the units that we have for our numbers. So we see 355 milliliters. Milliliters is a unit of volume, so I know that this is going to be my volume for my calculation. I also know that I don't want it in milliliters. I want that in liters. So I'm going to need to make a conversion in my denominator here in order to ensure that I have liters in the denominator. The second is that I was given moles directly instead of mass, so I don't have to do any conversions with that to make that into moles. So that can go directly into my numerator. The final thing is that the word molarity never really appeared in this question. Instead, I was asked for the molar concentration. So when you see language like that, you should be keying in that that's going to be molarity, and I need to have my moles per liter of solution. I plug in all my values, and I do this multiplication and then this division, and I would see that I get 0.375 molar sucrose in my soft drink. So dilution is really important in chemistry. It's fairly difficult to take a solution and make it more concentrated, unless you actually have pure solute to add. But it is fairly easy to add more solvent usually and make a solution less concentrated. And this is typically what is done. A lot of times a chemist is going to prepare a stock solution that's more concentrated than any solution he's going to need. And then he just adds solvent as needed to produce the solutions of specific concentrations. In this image, we can see kind of the effects of dilution. So both of these different solutions contain the exact same amount of copper nitrate, the blue stuff, but one of them is more concentrated and therefore has a darker color than the other one that is more dilute. And the more dilute one was made by adding more water, in this case, more solvent to dilute it down. The important thing that we need to be able to do is to calculate what the concentration is going to be after we do a dilution. And basically we can derive a formula by starting off by thinking about, we're going to limit ourselves to molarity here, but the molar amount of the solute, N, so the number of moles that I have, all right, is going to be equal to the concentration, so that's moles per liter, times the liters of solution of that solution that I have. Okay, so if I know the concentration of a solution, I multiply that by the volume of that solution, then I can figure out how many moles altogether of a solute I have. We can write an expression like this for the two conditions, one before we've made any dilution, so when I have my more concentrated solution, and then a second expression for when after I've done that dilution, I have my more dilute solution. So the important thing to realize is that when I'm diluted, I haven't reduced down the amount of solute at all. N1 is going to equal N2, okay, which means that I can make a substitution into this equation where M1L1 is equal to M2L2. So the concentration of my initial solution times the volume of that solution that I diluted is going to equal the new concentration of the solution times the volume that I wound up with. Okay. We showed this for the case of molarity, where we had molar concentrations and volume, but this can actually be generalized to any concentration unit. All right, and we're going to talk about some alternative concentration units in a little while. So in general, it's always going to be true that you're going to have C1 V1 equal to C2 V2. This is going to be our dilution equation. Let's take a look at an example of a calculation like that. And a lot of students are going to shut down when they kind of see one of these kind of questions, just because there's a lot of numbers thrown at you. And the important thing is to really just remember that it's a fairly simple equation, all right? And to just make sure that you are matching them up appropriately when you're plugging them into the equation. So let's take a look at this. If 0.850 liters of 5 molar solution of copper nitrate, this stuff right here, is diluted to a volume of 1.8 liters by the addition of water, what is the molarity of the diluted solution? First thing I'm going to notice is that I was already given it in this concentration unit is in molarity, so I don't have to make any adjustment to that to get molarity out. All right, so the concentration unit you're going to put in is going to be the same as the concentration unit that you get out. I'm going to notice that I have 0.850 liters of this copper nitrate, so those two are going to get matched together here. All right, so I'm going to have 5 molar, 0.85 liters of solution is going to go there. On the other side, I'm being asked for the concentration, so that's C2 is what I'm going to want to solve for, all right? And how much of the C2 do I have? I have 1.8 liters right here. So I think about plugging those in, and then I solve for C2 because that's what I'm going to be asked for, and I get this expression right here. And I think that this is one of the best places to really check yourself when you're plugging into this equation here, okay? Because if you think about it, you're diluting this solution, meaning that your concentration should be going down. All right. So you had a choice. I could have put 1.8 liters up here, 0.85 liters down here, or I could put 1.8 liters up here and 0.85 liters up here. I need to have the smaller volume in the numerator and the larger volume in the denominator so that when I do this math, I wind up with a smaller concentration. Okay. So that's a nice little check for you if you think about what's happening in the problem to know that you've placed those volumes in the right place. You can also know what I said before about the concentration, because these liters canceled, you're going to wind up with molarity in the end. Now, it would be necessary that if these weren't both in liters, okay, to make sure that they did have the same unit. And while it is important to have them in liters when you're calculating molarity, it's actually not important to do that in the dilution calculations. Okay, this could be in milliliters and this could be in milliliters. Just so long as they have the same volume unit and they're canceling, it'll still work out numerically to be the same thing. I do always suggest that you do just convert everything to liters right off the bat, because it's just the safer route, and it's going to work for all of the problems. But so long as those units are canceling here, this type of problem will work out.